Na biya ba sako class na pas pa ba sako. Okay, now I think we are recording also. CR? Hello?
Yes, sir. आवाज आ रहा है sir.
Yeah, okay, we have started the recording also, so it is recording now. Okay, so now for a planar structure, what we have now, kinematic indeterminacy equation will be 3j minus r plus I. What is the j now? Number of joints. From where these three are coming? Three are coming from the freedom. If a joint is free now, it will be having 3 degree of indeterminacy, 2 translations and 1 rotation. J is the number of joints minus R now. R is the number of reactions here. You can see in the origin now R is equal to number and I is equal to number of internal hinges. So this will give you the kinematic indeterminacy. And already I explained this, that first you consider all the joints as free. So 3 times J now, this will give you the total possible now kinematic indeterminacy of the structure. Then we go after the number of reactions now. So when we include them with the negative sign, because you will be now subtracting because of these reactions the number of indeterminacy. So 3j minus r. And if you have an internal condition, so plus 1 also we include. If you remember what was I in case of the internal hinge, what was the kinematic indeterminacy? Instead of 3, it was 4. So because of that, now including the number of hinges now. So now if we ignore the axial deformation, what will happen? If we ignore this axial deformation, then the kinematic indeterminacy will decrease. And why we are ignoring? Because I'll answer this, that these effects are negligible in case of the beams as well as in case of the frames now. Now, kinematic indeterminacy after ignoring the axial deformation is 3j minus r plus I, which is coming from this top equation, and minus the number of members. Now, with the examples, now we will move and we'll go now through these equations, and by observation also we will do. Now coming to this one on the top, now you can see in this white area we are looking at the structure now. It's a cantilever beam now. At the left we have a fixed support, at the right we have a free support now. Now the numbers written here 0 and 3, these are not the joint numbers. This 0, it is showing you the kinematic indeterminacy at this left joint, and 3 is showing you the kinematic indeterminacy at the right joint, which is free now. Why 0? Because it can resist vertical, it can resist horizontal force, and it can resist the moment also. So no chances of vertical translation, horizontal translation, and rotation. So that is why here it is 0. Why it is 3 here? If you follow this cursor now, this is the deflected shape now. So it will be having vertical translation, it will be having horizontal translation, and it will be having a slope also, rotation also. So the kinematic indeterminacy will be simply now the addition of these joints degree of freedom, which is 0 plus 3 here, and it is written here 0 plus 3, which is equal to 3 now. If we ignore the axial deformation, axial deformation means along the length of the member, it cannot deform now. So means this horizontal translation at this joint 3 we will be now taking away. When we remove this, it will become now one member is there only, so it will become 3 minus 1, so 2 degrees it will become kinematically indeterminate. Now, if you solve it as a 3 degrees indeterminate problem, and let's you consider the manual calculations now, so lot of efforts you will be needing instead of if you compare it with the 2 degrees indeterminate problem. And why we are doing it? Again, the reason is that the axial effects are negligible. Now, if we go by equation now, equation, how can we do it? We have two joints now. So J is equal to 2, we are writing. Number of reactions now, at the fixed support, we have 3 reactions. So R is equal to 3, but we are writing. What was the basic equation? There is no hinge now. So it means 3J means 3 times 2 minus R. So minus 3 is equal to 3. So by observation, it was 3. And by this equation, it is 3 now. If we ignore the axial effect, so means it is 3J minus R and plus it was 3J minus R, and it was minus the number of members. So minus one member is here. So 3 minus 1, it is coming 2 again here, which you can see here. So by observation is the top now line, and by formula we have this bottom line, and both are matching now. Similarly, if we go to this second now diagram, and second diagram, at the left we have hinge support, at the right we have a roller support. It is a simple beam condition, simply supported beam condition. Now, at the left support, we have 1 degree of freedom, which is rotation here. The beam is going to rotate this way. So we will be having only this rotation here as unknown. So that's why 1 is written here. At the right support, we have translation in the horizontal direction, and we have a rotation here also. So that is why 2 is written. The total kinematic indeterminacy of this simply supported structure will become 3, which will be coming from 1 plus 2, which you can see here. 1 plus 2 is equal to 3. If we ignore the axial effect, means we will be taking away the effect of this one member. So this will become 3 minus 1 is equal to 2. Now again, if we go by the equation now, so we need to find out the number of joints. So the number of joints are 2, left support and right support. The number of reactions are 3, R is equal to 3 written here. 2 are coming from this left support, vertical and horizontal reaction. And then 1 is coming from the right support, which is the vertical reaction. So here you can see R is equal to 3. Now kinematic indeterminacy, if we take the total kinematic indeterminacy, including the axial effects, so this will become 3J minus R. So 3 times 2 minus 3 is equal to 3 degrees. This is kinematic indeterminate by 3 degrees. But if we ignore the axial effect now, so the axial effect, if we ignore, it is becoming now 3 minus 1. This one is coming from the number of members. So this is becoming 2 degrees. And what are those 2 now degrees? Where are those 2 movements now? The possible movements, one is rotation at left support and one is rotation at the right support. In the direction of the member, the structure is not going to move now. That displacement we are ignoring. So theta at left support and theta at right, theta L and theta R are going to be our kinematically indeterminacy. Those are the degree of freedom. Coming now to the third diagram, it is a 2-span having 3 supports now. At left, we have hinge support. In the middle, we have a roller support. And at the right also, we have the roller support. Now, at the left support, we have one unknown displacement, which is rotation. In the middle one, we have a rotation as well as we have a horizontal translation. And at the right support, also we have a rotation as well as the translation. So here now you can see the summation. Those unknown joint displacements are written at the top of these joints now. 1 from here, 2 from middle, and 2 from the right support. So 1 plus 2 plus 2 is equal to 5 degrees. This is the total kinematic indeterminacy of the problem. Now, if we see that this is a beam problem, axial effects are not going to be more, so we can take away or we can ignore the axial effects. Now, by removing the axial effects, what do we mean? We need to take the number, simply the number of members from here, which are 2. So this is becoming 3 degrees indeterminate problem. And when we solve this by using the 3 degrees indeterminate problem, we need to identify those 3 degrees, and those 3 degrees will be rotation at the left support, rotation at the middle support, and rotation at the right support. Now, those will be the indeterminacy, and those will become our unknown quantities. So we will designate them D1, D2, and D3, and we will initially assume its direction also. It will be your choice again. You will be having the freedom. So usually I assume initially clockwise as my clockwise rotation as my positive direction. Or if you go by the equation now, so number of joints we have 3, this left, middle, and right joints. Number of reactions 4, 2 from the left, 1 from the middle, and 1 from the right support. So 3j minus r is equal to 5. And if you see both by observation, by this equation, they are matching. And most of the time, remember, we engineers are in the middle of so many equations and formulas, so that we cannot recall sometimes these equations. So by observation, it is a good practice to find out these indeterminacies. If we ignore again the axial effects, which are coming from the 2 members now, so this is again 3, and you can see here 3 is matching with this 3. If now we have this final diagram now, from the final sketch, what do we see now? 1 degree is coming from the left support, which is a hinge support. Then 4, according to the definition now, is coming from this middle, which is a hinge, internal hinge. From where this 4 is coming, we have 2 rotations and 2 translations now. And from the right support, which is a roller support, we have 2 kinematic indeterminacy. One is horizontal translation and one is rotation here. And now let's discuss why we have at hinge now these 4 degrees of indeterminacy. This hinge is in the middle now. This structure is unsymmetrical. Let's this hinge, instead of the middle, we push it to the left now. Let's bring it to this 1/4 position of this total span. Let's, instead of this we bring it here. Now, if we load it, what will happen? It is going to deflect this way now. If you are looking at my cursor now, so it is going to deflect here down, and from here it is going to go up now to this support now. Now, what will be the rotation here? The rotation here will be this vertical displacement divided by this horizontal distance. And for the right hand side, it will be this vertical divided by this horizontal. Now, vertical is the same, but the horizontal distances are different now. So means the rotation of the left member will be different from the rotation of the right side member. And that is why we have 2 rotations unknown at the support. If now the structure is perfectly symmetrical and this hinges in the middle location, then you can say that both rotations will be the same. So if we find one rotation, the other one will be automatically found. So in that case, you can say because of the rotation, we have only one rotation unknown. But if it is unsymmetrical, then the left hand side rotation will be different for the right side member. So that is why we have 2 rotations and 2 now translation. One will be vertical, and this, because of this settlement and rotation, horizontally also it will be changing its location. So we have 1 vertical and 1 horizontal translation. So 2 translations and 2 rotations. That's why the total indeterminacy of an internal hinge is 4 degrees. Again, by simple addition of these individual joint displacements, when we sum them up, we get the total indeterminacy. And if it is given that ignore the axial deformation, so what we have now, 7 minus 2 is equal to this 5 degrees. From the equation, again, you can see the verification now. So 7 degrees and 5 degrees here by using this equation. Coming now next to the case of the, now next is going to be the frames now. Frames, we will use the same concept. On the left hand top side, you see this one bay and one story frame now. The bottom joints are having supports now, and those are fixed supports. At the top, we have free joints, free rigid joints now. So here we can say easily that its kinematic indeterminacy is equal to 0. The bottom right support, this joint also, it is giving you 0 degree kinematic indeterminacy. Top left 3 degrees, and this top right, it is also giving you because those are free rigid joints. So 3 plus 3, it means it is a 6 degrees indeterminate problem. Or you can go now by the equation. What was the equation? 3r minus 3j minus r is equal to 0 to find out the total indeterminacy. So the number of joints, if we count, so 1, 2, 3, 4. J is equal to 4. Reaction 6, 3 from this support and 3 from this support. So R is equal to 6. 3J minus R, so this is giving you 6 degrees. If we ignore the axial effects, we need to take the number of members. 3 members we have, so 6 minus 3. This is becoming 3 degrees indeterminate problem. Similarly, you can apply the same to here, to this structure and this structure also. Simply, if we go by the total indeterminacy, so number of joints 1, 2, 3, 4, 5, and 6. This hinge is also considered as a joint now. So J is equal to 6, we are writing. Number of possible reactions, 2 from the left support, 2 from the 1 from this roller support. So reactions we are writing 3 now. Internal hinge we have 1, so 3j minus r plus 1, so this is becoming 16 degrees. And if we want to take away this number of these members, so 16 minus 5 is should be coming 11, 16, 11, not 8. So this is 11 degrees indeterminate problem. Similarly, here you can count the number of joints 1, 2, 3, 4, 5, 6, and 7. So J is equal to 7. Reactions 3, 2 from this one. So 3 plus 2 is equal to 5. Then we have 3 from here, 8, 2 from here. So 10. And then 1 from this roller support in this direction we have a, so this one 10 plus 1 is equal to 11. So we have R is equal to 11, and we can use this equation. This is becoming 10 degrees. Then we need to take away, if we ignore the axial effect, the number of members. So this reduces to, you can check it, 4 degrees. Now, you should be in a position with this much discussion to find out the kinematic indeterminacy of a structure very quickly. Now, if I look at the time now, the time is 9:15. So still, I think we go for 15 minutes and then we take a break. Now, general procedure I'll be discussing now. And if you have this general procedure of the flexibility in mind, you should not be facing any difficulty in understanding this process. This is just the reciprocal of what we did in the flexibility method. This method is also called displacement method, and you know the reason why displacement, because displacements are our unknowns. In this method, the degree of kinematic indeterminacy is determined. Why we are finding out the kinematic indeterminacy? Because we are finding out the unknown displacement. So from where the unknown displacements will be coming, it will be coming from the degree of freedom, which is also the kinematic indeterminacy. And the displacement components are identified. A coordinate is assigned to each independent displacement. Now you will have to label now each independent this displacement. If you remember, we labeled the unknown now reactions, redundant actions. And what was its labeling? It was AR1, AR2, AR3, and so on. So here now we will be now labeling them as D1, D2, D3, and so on. D is the unknown giant displacement. So thus D1, D2, D3, and Dn are the redundant displacements at 1, 2, 3 up to n location. If all the redundant displacements are restrained, unknown giant displacements, what we do, we restrain them. And how we restrain them? Just by locking that capability. If it was free to rotate, so we will stop that rotation. Let's we have a hinge support. So at hinge support, how can you stop the rotation? You just provide a fixed support there. If we provide a fixed support there, it means we are restraining the rotation now. So first we show, let's say it was one location. So at one location, the corresponding unknown uh, displacement was rotation. So we designate this by a curved arrow and we label it as D1. So we show it, okay, this thing we are going to lock now. And then we come in the kinematic determinant structure, and instead of the hinge support, we put a fixed support now. Now, fixed support, if you fix something, it means you are stopping both translations and a rotation. But by that level now, D1, you are showing that, okay, originally already those two translations were stopped. But now by providing this rollers, this fixed support, we are only restraining the rotation. So this will be restrained up. Now, if you look at the terminology in the flexibility method, this structure used to be a release structure. What we were releasing the redundant actions, which was the reason or cause for making the structure statically indeterminate. So we were releasing those redundant in order to make it statically determinate structure. But here now, the structure is kinematically indeterminate. So how can we make it determinate? If we stop these unknown displacements, and how we can stop them? If we restrain those locations, those displacements. And the resultant structure now will be known as restrained structure. Now somebody can ask you in an interview that, do you know release structure? So you say, oh yes, I know it. If when we remove the redundant actions, the structure obtained is known as release structure. So he can ask you, okay, now come on, you tell me what is now the parallel in case of the stiffness method now. So you can say we call that kinematically determinate structure as a restraint structure. Why restraint structure? Because we are restraining the unknown giant displacements. And this will be also known as basic kinematically determinate structure. So identification of the unknown giant displacements, labeling them now with D1, D2. This is going to be our general notations for the unknown giant displacements. And then locking them in order to get the basic kinematic determinate structure, which is also known as this restraint structure. So these are the steps, initial steps now. After this now, what happens now? It first requires the stiffness method analysis satisfying equilibrium equations. Now, originally, if we take example of the hinge support, moment at hinge support, straight away you say it was zero. But when you log this by making it a restraint structure, so what will happen? Moment will generate there. So it means the equilibrium equation is not satisfied as that of the original structure. Because of putting this constraint now, we are having a moment which is violation of the equilibrium equation, equilibrium condition. So what we do now to do this, the unknown displacements are written now in terms of the loads. Because of the hinge support, it was rotating by certain amount. And because of that rotation, moment was zero. Now, when you are not allowing the rotation, it means you will have to put the moment there. Now, how much rotation we should give to bring it back to the zero rotation now? So we need to find out now, apply that much now rotation now. Now, to do this, the unknown displacements are written in terms of the loads by using the load displacement relation. So what we do now, we write the load displacement relation. Then these equations are solved for the displacements. The only unknowns in the equations now will be the displacement. If you look at now again, we will be having now four now parameters. One will be AD, which you can see here in the orange. It is now corresponding to the DRS now. AD, it will be the action corresponding to the displaceable now joint. ADL, it will be the corresponding action corresponding to the displaceable joint under the actual loads. L is coming from the load. S, so this ADL is actually, it is corresponding to the DRL matrix now. And here S, it is corresponding to F matrix, stiffness coefficient matrix. D, it used to be AR in the previous method, unknown redundant action. Here it is the unknown joint displacement. So you see the similarity in both the methods. Now, once the displacements are obtained, the only unknowns in this equation will be the displacement now. The rest three parameters will be known now from the load displacement, these relations. So once the displacements are obtained, the unknown loads are determined from the compatibility equations using the load displacement relations. Now for n independent displacements, you can write this AD1 is equal to this one, AD2, ADN, as we develop the compatibility equations now. And these equations now we are putting now actions in equilibrium. So these are known as equilibrium equations. So this is also known as equilibrium method. This stiffness method, it is also known as equilibrium method. The flexibility method was also known as compatibility method. Now, when we get these simultaneous equations, why we have n simultaneous equations? Because the degree of kinematic indeterminacy was n. So we will have n. If the kinematic indeterminacy is 2 degrees, so we will have 2 simultaneous equations. If it is 3, we will have 3 simultaneous equations. Now, these simultaneous equations, we can write this in the matrix form. So AD matrix you see on the left hand side, what will be the order of this? It is always going to be a column vectors, and its order will be n cross 1. Why n? N is the number of degree of indeterminacy. So an ADL matrix is always going to be a column vector. Its order will be again n cross 1. Stiffness matrix, it will be order of n cross n. Here you can see n cross n. It is always going to be a square matrix. It's always going to be a positive definite, and it is always going to be a symmetric matrix. Means 2, 1 will be equal to 1, 2. 1n is going to be equal to n1, and n2 is going to be equal to 2n, and so on. And D is always going to be a column vector, and it is again going to be n cross 1. So we will be having n rows and 1 column. Now we can write this now in condensed form, and in condensed form it will become AD is equal to ADL plus S times D. And in the orange, in these subscripts, you can see order of the matrix. So n cross 1. ADL is also n cross 1, S is n cross n, and D is equal to n cross 1. Now, to solve this for the unknown joint displacements, now we keep this on one side. So we take this ADL to the left hand side. So it becomes AD minus ADL, which you can see here. We divide both hand sides by this n. So this becomes S inverse now. So D final equation, we have D is equal to S inverse times AD minus ADL. Now, again, this final equation, you can compare it with the flexibility matrix method. In flexibility method, what we were having, instead of D, we were having AR, and it was equal to F inverse instead of this S inverse. It was equal to DRS minus DRL. So we have the same pattern here also. But instead of the now unknown giant displacements, here we are looking for the actions corresponding to the displaceable joints. Now you can see now the definition of these various terms, four terms we have. So AD, it is the external actions corresponding to this displaceable joint, the joint displacement. So this will be the external action. There we were looking for the precondition because of the settlements. If you remember, if something was corresponding to the redundant action, we included those into the DRS matrix. So here we will, the external action corresponding to the unknown giant displacement, we will be including in the AD matrix. A is for the action and D is corresponding to the, D is for the displacement. So action corresponding to the displacement. Which one? Displacement, unknown giant displacement. Next, ADL, now again action corresponding to the displaceable joint under actual loads. So action corresponding to the displacement joint in the restraint structure due to applied loads. And these will be fixed end actions. Just by having now for the normal condition, you need to now remember what kind of fixed end action is going to produce. So we will discuss the general cases for this one. In case of the flexibility method, it was very hectic. How it was hectic? Look, if you need to find out displacement corresponding to the redundant action, so you need to apply the unit load there, then drawing the conjugate beam. Let's we were using the conjugate beam method there. So conjugate beam, then loading the conjugate beam with the M over EI diagram. Then if you are finding out the settlement in the actual structure, so you need to find out the shear in the conjugate beam at that particular point. And if you are finding out, let's say, settlement or deflection in the actual structure, so you need to find out moment at that particular location in the conjugate beam. So a lot of calculations were involved there. Here, just for the specific case, you will be, with the help of the established equations, quickly you will be finding out the member and actions, and quickly you will include them as a ADL matrix. Similarly, if you were using the unit load method now for finding out the displacement, so again, that if you remember the writing the moment equations and then the combination summation of integral of capital M times small m times dx divided by EI. A lot of work was involved there, but here it will be going, it will be real quick now. So I'll be giving you the general equations how to find out quickly now the member and actions produced under the loads are for the displacements also. I'll give you the quick equations. If you rotate one end, so how much actions will be produced at that particular end and at the far ends also. Or if you give translation now, let's say at one end, so what will be the actions produced at both ends? So I'll be giving you that condition also. Now D, it is the unknown giant displacements, and S, which is the stiffness coefficient, that is, it is force required to produce unit displacement. This definition here, this statement is wrong. Displacement per unit force, that was the definition of the flexibility. So you need to be careful and don't get confused with these definitions. So here it is the force required to produce unit displacement. So that is the definition of the stiffness. Now, stepwise solution procedure using stiffness method. So stepwise now we'll go by how we go stepwise. Now, the following steps must be followed while solving a structure using stiffness method. Step number one. Step number one is we make the structure kinematically determinate. So how can we make the first we look at the displaceable joint. We identify them, we label them that okay, these are our unknown joint displacements now. And after that, we come and we make the structure kinematically determinate. Now by restraining the joints, so we will restrain the joints. We identify the redundant joint displacements, we restrain them, and the structure obtained is known as restraint structure now, which is the basic kinematically determinate structure. Now, when we identify the unknown joint displacements, we look at the same locations, the corresponding now actions, where the structure is having some externally applied actions corresponding to those displaceable joints. And we include them as our AD values. And that way we construct our AD matrix. So here now construct the AD matrix from the actions corresponding to the redundant joint displacements. Now you can now go back now and make the resemblance now. What is the resemblance between this step one and what is the resemblance in case of the flexibility method? In case of the flexibility method, what we used to do, statical indeterminacy, here we are finding out the kinematic indeterminacy. There we label our redundant actions. Here we label our redundant displacements. There we find out the AD corresponding to the AR. Here we find out, there we find out DRS corresponding to the redundant action. Here we will be finding out AD corresponding to the displaceable joints now, the unknown joint displacement. So AD will directly be coming from your displaceable joints now. These will be the actions. Step number two now, what we do now, apply the actual external loads on the basic kinematic determinate structure and find the actions at the locations of the redundant joints, and those actions will become now, which will be the fixed end actions. This will become your values of ADL matrix. Again, you can see the resemblance. What you used to do in case of the flexibility method, the basic determinate structure, which was release structure, it was subjected to the actual loads. Here, the basic kinematic determinate structure will be subjected to the actual loads. There, we used to find out now the displacements corresponding to the unknown redundant actions. Here, we will be finding out now the fixed end actions corresponding to the unknown joint displacements. So here we are finding out actions, there we were finding out the displacements. Step number three now, there we used to generate the flexibility coefficient matrix, and how that was generated, we applied the unit action corresponding to the redundant action. Here, the stiffness coefficient matrix will be generated. How it will be generated? We will apply unit displacement now corresponding to the displaceable joint, the unknown displacement. So apply the redundant joint displacement on the basic kinematic determinate structure. Now, to standardize the procedure, only a unit displacement is applied in the positive direction, and this will generate the stiffness coefficient matrix. So stiffness coefficient matrix is generated. And how we generate it? We apply a unit displacement now in the positive direction and find out the member and actions generated. How much member and actions are generated. The corresponding member and actions we take, and that gives us that specific stiffness coefficient value. Now, when we have these numbers now, we got now the AD values. we got the ADL values, and we got the stiffness coefficient S values, means only D is unknown now. So now we are in a position to write down the equilibrium condition. So the basic equilibrium condition equation is AD is equal to ADL plus S times D, or D is equal to S inverse times AD minus ADL. So right hand side values we have now, so we can find out the unknown giant displacement value. Step number 5, we go now when these displacements are known. Now the structure is becoming, it is now a basic kinematic determinant structure because the unknown giant displacements are known now. So what we do now, we know now next we go and we compute the member and actions. How the member and actions are going to be formed? The member and actions we designate again by AM, and this AM will be equal to AML as we did in case of the uh, flexibility method. Plus, there used to be AMR, but here now we will be having AMD now instead of AMR. And there AMR times AR, here will be AMD times D now instead of AR. So we'll discuss this in a moment. Now, I think this will be a good point to take a break now, and after this, we will start with the examples how we write these equilibrium equations. So it is now 9, almost 9:38. So let's consider, take it as 9:40. You should be back by 10 o'clock. Is it okay with you?
Yes, sir. Okay, sir.
Okay, 10 o'clock we will be starting again. Okay.
Okay, sir.
Okay. Bye.
Sir, recording on.
Os foram ligar fora. Fora. Fora.
څنګه یې اکبر علیا سجاد یہ کلاس کس ٹائم سٹارٹ ہوگی؟
کون سی کلاس؟ کون سی کلاس؟ 11 بجے اسٹارٹ ہوگی نا وہ ٹرانسپورٹیشن والی.
اسٹرکچر کی یار ابھی جو بریک ہوا ہے.
تو یہ ابھی اسٹارٹ ہوگی نا 11 بجے سر نے کہا 10 بجے سر نے کہا تھا تو بس یہ ہوگا نا. تو ذرا یہ ویڈیو آن کرو ذرا.
اوکے.
واہ یار تو بہت خوبصورت ہو گیا.
صدام ویڈیو بند کرو ریکارڈنگ.
روز شکل مت دکھاؤ.
یہ مہران کو کیا مسئلہ ہے؟
یار تیرے خوبصورتی سے جلتا ہے وہ.
میں نے کہا کہ ویڈیو بند کرو ریکارڈنگ میں ابھی تک بند نہیں کیے.
کیوں کیا ہوا ہے یار؟ ویڈیو سے کچھ گناہ تو نہیں ہے؟
ذرا اپنا چہرہ اپنا خوبصورت چہرہ.
پھر جب ہم دیکھیں گے تو آپ کو دیکھنے کی کوئی وجہ نہیں ہوگی آپ کو.
اب بہت کیوٹ نظر لگ جائے.
یار آپ تو جیسے یار یہ آن لائن کلاسز کا کچھ مزہ ہے یا ویسے دیکھتے ہو ویسے ٹائم ضائع کرتے ہو؟
بڑا بہت مزہ آ رہا ہے. پہلے ویک تو تھوڑا مشکل ہوتا تھا لیکن ابھی تو بہت مزہ آ رہا ہے. ہمارا ابھی تو ہم ایڈجسٹ ہو گئے اس کے ساتھ. ویڈیو آن کرو نا سدا.
کل یہ جو کل ہائیڈرولوجی اینڈ واٹر مینجمنٹ میں میری اٹینڈنس ہوئی تھی.
اگر پریزنٹ ہے تو ہو گیا.
میں تھا نا پریزنٹ تھا تقریباً 10 بجے تک پریزنٹ تھا. اس کے بعد نیٹ ختم ہو گیا تھا. اس کے بعد میں آف لائن ہو گیا تھا.
چلو مبارک ہو. تیرے سائڈ پہ نیٹ ہوتا بھی ہے کچھ؟
گزارا ہوتا ہے نا فیس تو دیش.
او ہر سنا کیسا ہے؟ تیرے بچے کیسے ہیں؟
بس بالکل سب ٹھیک ٹھاک ہے.
اچھا چلو شکر ہے. اس دن دیکھا ہوا تھا وہ
صدا میں
تمہاری فوٹو شوٹو لگائی ہوئی تھی تم.
صدا میں یہ شہر میں آ کے رہو نا. اس طرح نہیں ہوتا کہ آپ بس گھر میں بیوی کے ساتھ رہو گے اور پھر نیٹ بھی ہو وہاں پہ سب کچھ ہو اور پھر اس طرح تو نہیں ہوتا نا.
یہ ایسی بات نہ
نہیں
کرو سجاد.
نہیں
ہمارے دوست کی توہین
نیٹ
کر
کا
رہے ہو.
پاکستان میں نیٹ کا پرابلم ہے. وہ مسئلہ نہیں ہے.
انا سب de خلو ولا لاس كده.
چپ شکن ہے ابو ذرا.
تو سر کدھر چلے گئے ہمیں؟
سر کا کچھ پتہ نہیں ہے لیکن فیض یہ مجاہد صاحب کی جو اٹینڈنس اور اسائنمنٹ اس نے کہا کہ یہ سلائیڈ میں ہے.
نہیں نہیں وہ تو الگ دی ہوئی ہے. ای میل پہ سینڈ کی ہوئی ہے سر نے.
کہاں سے کریں گے کچھ اس کا آئیڈیا آپ لوگوں کے پاس ہے؟
پتہ نہیں میں نے تو ابھی تک دیکھی نہیں ہے. کھولی ہے تم لوگ کھول کھول کے ڈالتے آتے ہو. میں تو کبھی کھولتا بھی آخری دن کھولتا ہوں پھر حل کر کے دے دیتا ہوں بس.
قسم سے میں نے کچھ بھی نہیں دیکھا یار. ادھر بس گاؤں میں پڑھائی کا بالکل وہ نہیں ہے نا. بالکل ماحول نہیں ہے. ایک
ہاں
اوپر سے آن لائن کلاس. یہ بھی
ہمارے
ایک بہت بڑا پرابلم ہے.
ہمارے یہاں کون سا ماحول ہے؟
سجاد اور فیصل لوگوں اور یہ ان کو اور کوئی کام نہیں ہے. اکیل ہو گیا ہے. ان کو کہو کہ یار یہ جو اسائنمنٹ کیا ہے جس نے کیا ہے وہ مطلب فارورڈ کر دے تو سب سبمٹ کر دیں گے.
اچھا اس طرح کریں گے. ہاں یہ تو صحیح بات ہے یار. بہت صحیح بات ہے.
ہاں نا سجاد ادھر بہت بڑا مسئلہ ہے یار قسم سے.
Hello, can you hear me now?
Yes, sir.
Yes, sir.
Okay. And you can see my screen also.
Yes, sir. We can.
Okay, okay, okay. So let's start with this example number one now. Now, let's illustrate the above mentioned procedure with the help of this general example. If you look at the structure, at A, we have fixed support, at B, we have roller support, and it's loaded with UDL now having intensity of W. Now, the total indeterminacy of this structure is 2 degrees. How these 2 degrees at joint B, if you see it, can translate in the horizontal direction, and it can rotate also at this joint B. So these are the 2 degrees of indeterminacy. But now, if we ignore the axial effect, so this horizontal translation is gone now, and we are left with only rotation at B. So we take this kinematically indeterminate 1 degree. So one redundant joint displacement should be chosen, and there's unknown joint displacement here. I show this on the second sketch, which is D now. In the clockwise direction, we are taking this as positive. So this D is for the unknown joint displacement. As there is only one, so with this general D I am representing. If we have so many, then we start labeling them by D1, D2, D3 up to as much as we have. So step number one will be selection of redundant joint displacement, which is rotation at B, and it is taken as independent joint displacement. So this rotation at B, which is D now, we take this as our unknown joint displacement. This is the one kinematic indeterminacy. How we make it kinematically determinate? We just put a fixed support here. So basic kinematic determinate structure you can see, which is the restraint structure. Now it was already fixed at A, and at B, this roller support, we are changing this to this B. Let's, if we include the horizontal translation also, so what we do, this rotation we show by D1, and this translation in this direction, we show an arrow now, and we designate that by D2 now. And this restraining structure now, we have two unknowns, which is rotation and translation in the horizontal direction. But as we are ignoring the axial effect, so it means it is 1 degree, which is rotation here. Now, when we restrain it here, originally, if you see, moment at this location was equal to 0. But now when we put actual load here, so here a moment will be generated, and we are violating this equilibrium condition now. Instead of 0, we will be getting some moment now value here. And we will have to satisfy now this equilibrium condition. So next slide, if we go now, we show now this restraint structure under the actual load W now. So what will happen? It is going to deflect this way now. And at B, we are getting now a moment. And whatever fixed end moment is coming here, that is becoming our ADL value. This will be the ADL value. In the previous now, if we go, whatever corresponding action we have here corresponding to this unknown joint displacement, if we have an action here, so that is becoming our AD value. But we don't have any, so that in this case, it will become equal to 0. So this is how we make the AD and then ADL matrix. Now, in original structure, we were having some now rotation here because of the roller support. It was allowing rotation. How much rotation now we should have here so that we generate an action, which is moment in this case, which is equivalent to this M moment now, which is equivalent and opposite to this in nature, so that when we add up this moment generated and this moment generated, we get the final moment, which is 0 in this specific case. So this way we can put this joint in equilibrium, and for this we need to write down the equilibrium equation. In the previous, if you remember, in flexibility, we removed the redundant action, so we end up having a displacement here. So we were violating the compatibility condition. Originally it was 0, but now by removing the redundant action, we were having displacement here. So what we did, we applied now action in such a way so that we brought it to the original 0 position. So that displacement was in the opposite direction, whatever was produced by this actual load now. And we add up all these two now numbers, all these two displacements to get the effect of the original structure to satisfy the compatibility condition. Here we are now in terms of the actions, we are satisfying the equilibrium condition. So step number 2, what we do, we determine the ADL matrix. How we determine it? We basic kinematic determinant structure we put under the actual loads and we compute the ADL matrix. After this, we come and find out the stiffness coefficient matrix, and how that is found. The basic kinematic determinant structure acted upon by unit value of redundant joint displacement and computation of stiffness coefficient values. Now what happens, initially we put this to the unit displacement and multiplied by the actual displacement, we find out the whatever member and actions are produced, and that is becoming our stiffness coefficient matrix multiplied by the actual displacement. Now when we have AD and ADL and stiffness matrix, the only unknown is now D now. So we write the equilibrium equation. Now we rearrange this and find out the unknown joint displacement by using this equilibrium equation. And this way we find out the unknown joint displacements. When the unknown joint displacements are known, the structure is becoming kinematically determinate problem. Now there is a very nice relation if we give rotation at a joint and keep the other one now fixed support the other end. So this rotation is having a very nice relation with the moment produced here, to the direction of the movement and to the amount of movement. How and what is that? We will discuss that in a moment now. Now, when this action is generated in terms of the moment now, how it is going to be transferred to the far end. So again, we have a very nice relation. Now, because of moment generated at the near end and at the far end, near end which is near to the end at which we are providing the rotation, and the far end is the other end which is away from this end. So at the near end and at the far end, when we know the moments, what we can do, that is becoming our total unbalanced moment. We need to keep the structure in equilibrium. So what we do now, we apply a balancing couple now. The balancing couple direction will be opposite to this applied now unbalanced moment. And its magnitude will be simply the summation of this unbalanced moment divided by the distance between the two ends. So this way we can find out these forces, which are the reactions at this A and B now, the magnitude of those reactions. Those reactions will be making a couple now. Couple means will be same in magnitude, but opposite in direction. And we'll be having this perpendicular distance between them. So this relation we will discuss in a moment now, when rotation is given and when settlement or when deflection is provided at an end, then how these four member end actions will be generated. Now, comparison with this now, we are in a position now to go one by one and compare this flexibility method and the stiffness method. Comparison between flexibility and stiffness method. Now, flexibility method, what we do first, we determine this degree of statical indeterminacy. Now, parallel to this, what we do in case of the stiffness method, we determine the degree of kinematic indeterminacy. In flexibility method, we choose the redundant actions now to obtain the basic determinant structure. And in stiffness method, what we do, we choose the redundant joint displacements. Instead of actions, redundant actions, we find out the redundant joint displacement to obtain the restraint structure. Here we were obtaining the release structure in flexibility method, but in stiffness method, we are obtaining the restraint structure. Now, corresponding to those redundant actions in case of the flexibility method, we were finding out DRS values. But in case of the stiffness method, corresponding to the redundant joint displacements, we will be writing the AD values, actions corresponding to the displaceable joints. You can see now in the sketches, A, B beam is given. Statical indeterminacy was 1 degree. Only the vertical reaction V at B, we took that as a redundant action. And now parallel to this, the same beam now, but here the kinematic indeterminacy is 1 degree. And what is that? It is rotation at B now, as we discussed. Now assign coordinates to these chosen redundant. So AR is here and D is here. So we assign these now coordinates to these independent redundant actions and redundant displacement. Now, third one, what we do now, in the release structure component, the displacement DRL coordinates due to actual loads. Release structure, it is under the actual load, and we find out this DRL now, which is the displacement corresponding to the redundant action in the loaded structure under the actual loads. In case of the flexibility method, what is now the parallel process? In the restraint structure now, this was in the release structure, here it is in the restraint structure. Compute the actions which are ADL values at the coordinates due to the load other than those acting at the coordinates. Now, acting at the coordinates, where we include them in the AD matrix. So that is why you don't need to re-include it in this matrix. You will have to exclude it. So that is why clearly it is written that whatever is corresponding to the unknown joint displacements, you exclude it from the ADL matrix. Where we include them? We include them in the AD matrix. So here now, at this location in the clockwise direction, we were having now our D value, unknown joint displacement. So this is now the corresponding fixed end action, which is MB, and that MB value will be equal to ADL. Now we have a very simple equation now. If this throughout UDL is W, if we have the span value, so what will be the member end moment now? The member end moment will be equal to WL square divided by 12. So if W value is given, L is given divided by 12. So very simply you can find out this ADL. You don't need to go through all those conjugate beam method and maybe the unit load method, which we did in case of the frames. So you don't need to straight away, if you know the equations, you just plug in W and L values and find out the ADL value. Again, you will have to look at the direction of the movement. If this movement is matching the direction of the D, which you assume that is your positive one now. So if both are matching, it will be positive. If not matching, it will be negative. Now at B, let's say another member is connected from the right hand side. So you will have to sum up now the effect of both moments. Fixed end moment from the BC span will be also coming. And we take the algebraic sum of these moments, and that is becoming then our ADL at this location. We'll discuss this scenario. Now, step number 4 is in the release structure, compute the displacement at coordinates due to unit redundant action. And thus that is construct F matrix. So in the release structure, we go turn by turn. We subject this to the redundant unit action corresponding to the redundant action, and we start finding out the flexibility coefficient values. Instead of now unit action, here we will be subjecting the structure to the unit displacement. Now here you can see theta is equal to 1, and again this rotation you see it is corresponding to the D now in the same direction. So whatever member and actions are generated, we include that as a stiffness value. So here you see the moment will be corresponding to the D. So whatever M because of this unit rotation is coming, we include that as a stiffness coefficient, which is S value. So this way we construct the stiffness matrix. Now from the previous slide, we got the AD value corresponding to the displaceable joint. From this top one, step number 3, we got the ADL matrix. From here now we got this stiffness coefficient. If we multiply this by the actual displacement now instead of D now, so that will become now stiffness times the actual displacement. So that actual displacement is actually our unknown now. With the 3 quantities known, this one unknown, we can solve the simultaneous equations now. Simultaneous equations which we are making from the equilibrium now. So in next slide, we are going to now see, here we were writing the compatibility condition, and compatibility condition was DRS was equal to DRL plus F times AR. And here now, equilibrium equation, and equilibrium equation AD is equal to ADL plus S times D. You can compare now each and every term. Here we have DRS, this is displacement in the release structure corresponding to the restraint action, and this is the S was from the settlement. This is the precondition. Any precondition if settlement was given, so we include it, which is corresponding to the redundant action. Here it is action corresponding to the unknown giant displacement. Here it was displacement because of the settlement in the release structure corresponding to the redundant actions. DRL, it was displacement. Here ADL, it is now the action corresponding to the unknown, which is displacement. F was the flexibility coefficient matrix. Here S is the stiffness matrix. AR is the redundant action. Here D is the displacement. Here the AR was the only unknown, so we keep it on the left side and find out with the help of the known quantities. This was the final equation. Here displacement is the unknown, so we can keep it on the left side and find out with the help of the 3 other known equations which are here. So stiffness inverse AD minus ADL. Rest of the 2 procedures are the same. Step 6, we find out the member end actions. Similarly, in stiffness method, we find out this member end actions. And then when the member end actions are formed, in case of the beams, these will be the member end moments, and these will be the shear values. So 7, we go and draw the shear force and bending moment diagram. So this is also the standard normal procedure. Now example 2 now, that was 1 degree indeterminate problem, and we wrote a single simultaneous equation. Very simple equation, and we wrote this. Now we look at this one. Again, we are ignoring the axial effects now. So if you look at rotation at B, it is unknown, and rotation at C is unknown. So this is 2 degrees indeterminate problem. How we are going to formulate this? Here clearly it is written kinematic indeterminacy is 2 degrees. If we include the axial effects also, so then it is 4 degrees indeterminate problem. But again, axial effects will be negligible, so this is 2 degrees. Theta at B and theta at C, these are the unknowns. Now clearly we show them on the structure now, that D1 rotation at B and D2, which is rotation at C, these are our unknowns, and here we write them in the matrix form. Corresponding to this, in the actual structure where we have loads P1 and P2, we don't have any moment at joint B, we don't have any externally applied moment at joint C. So corresponding to D1 and D2, we don't have any externally applied actions. AD1 and AD2, we declare them equal to 0. So this way we construct our AD matrix, which are 0 and 0 in this case. The moment at C was in the counterclockwise direction and it was 1 kip-foot. So AD2 will become our -1 now. Why minus? Because it was opposite to this D2. D2 was in clockwise and this is in the counterclockwise direction. But here as we don't have that condition, so we put this equal to 0. So rotation it. Now instead of write down theta B and then theta C, I'll prefer to make them D1 and D2. Why? Because if we include the translation also, so should we go then with delta B and delta C? Or let's say we have so many charts, so how we cover them with B and C then? So the general notation we can write in terms of the D1, D2 and so on. How we make this kinematically determinate? We just now replace this roller support by fixed support and roller support at DC also by the fixed support. Now what we are restraining here with this arrangement, we are restraining now the theta, which is D1 at B and D2 here at C. So we are restraining the other quantities were already restrained or we ignored them. So basic kinematic determinate structure now we have. Now this basic kinematic determinate structure which is shown here. Now it's the same thing like at B already we were having the fixed support. So now this fixed support you can split it into two fixed support. It is the same thing now. So this restraint structure, what we do, we put them under the actual loads, which was P1 and P2. So one way of doing this, you just show this B support if you don't want to split this. So you just show it in the middle, connected with A with the member, connected with C with a member, and then inside it you show arrow and inside you show arrow in this direction. So that way also you can do. Now, because of this P1 now and P2 and having span also, you will be having the member and actions now. But we are interested now in ADL matrix, and ADL matrix will be coming from where? These will be now the member and actions corresponding to the D1 and D2 now. So D1 was rotation at joint B, so we need to come at joint B now, and it was rotation, so to the rotation corresponding action is moment now, not this vertical force, not this reaction, not this reaction. These moments, these are corresponding to the D1, which was unknown rotation. So the algebraic sum of these two moments now, one moment is coming from MBA and one is coming from MBC. We need to add them up. How we fix their signs? If you look at the MBA, the left hand moment, it is in the direction of the D1. We assume the clockwise as positive. So this we take as positive. And BC, which is counterclockwise, opposite to D1 now. So we take this negative. We algebraically add them up, and whatever quantity we have, that is becoming our ADL1 value. Now ADL2, it will be corresponding to D2 now. D2 was again, it was rotation. So corresponding to the rotation at that particular coordinate, we should be looking for the action now. And to the rotation, the corresponding action is now moment. And moment is this ADL2. So whatever fixed and moment is coming here, if it is in the direction of that D2, we take it positive and we write its magnitude. ADL1 and ADL2, now the definition is written here. It is moment in the restraint structure under the actual loads corresponding to the redundant joint displacement 1. And ADL2, it is moment in the restraint structure and under the actual loads corresponding to the joint displacements 2. So from here we complete our ADL matrix. Next, now step number 3 will be generation of the stiffness matrix. If you recall, in case of the flexibility method, we generated the flexibility coefficient matrix, and how we did it, we applied a unit redundant action, unit value of redundant action. Here we will be applying a unit value of redundant joint displacement. So corresponding to D1 now we will give a unit rotation. So how we give it now, here now you can see. Now here the basic kinematic determinant structure, what we do now, corresponding to the redundant joint displacement location, we go and turn by turn give the unit displacement. First, a unit rotation is now applied at location 1 and it is prevented at location 2. So if you see here, this was location 1, you can see the coordinate 1 here. D1 was at this location. So corresponding to the D1 in the same now location and in the same direction, theta is equal to 1 we put. Now this will finding out the values of S11 and S21, which is the first column of the stiffness coefficient matrix. Now, as a result of this, how the member end actions are generated. If it is in clockwise direction, the moment generated at this near end will be also in the clockwise direction. And its magnitude will be equal to 4EI theta divided by L. From where this 4EI theta divided by L is coming, we will discuss this. But now you keep it in mind how this rotation is provided. First, this fixed support, we release the moment. How we release it, we make it as a hinge support. And at the hinge support, what we do, we provide a theta is equal to 1. So that hinge is not shown here, but with this red line, the rotation is shown that this support is rotated to this location. And as a result, the whole structure now, you see this is now the distorted shape of the structure. The structure is going to distort this way now. How the action will be produced, we start with the moment now. The moment will be equal to 4EI theta divided by L at the near end. And its direction will be the same as that of the direction of the rotation. Rotation was clockwise, so this moment produced from the left hand side now span, it will be in the clockwise direction. Its magnitude will be 4EI theta divided by L. The left span, hand side span I am discussing. Now remember, this I is the I of this left hand side span. E is the left hand side span. And again, L is also the length of this left hand side span. So 4EI theta divided by L. Direction, how we fix whatever the direction of theta is, that will be the direction of this moment produced. Now, to the far end, it will be carried over by half now. The carryover factor is half if the far end is fixed now. So because of the half now, it is 2EI divided by L. If it is 4EI, this will be 4EI theta divided by L. What will be the sign? Sign will be the same, whatever we have on the near end. It was clockwise, so this is also going to be clockwise. So the far end moment now we have, we will prove all these numbers now in a moment. If we give rotation, so what are the actions generated? Now the left hand side, let's balance this one now. Why we need to this independently? Because this was fixed support if we take. So now clockwise direction, it has to be balanced by the counterclockwise couple now. So this is how we fix the directions of these reactions now. Counterclockwise, this will be downward, this will be upward. How we find out its magnitude? It will be simply the summation of these moments. So we have 4EI plus 2EI, so means it is 6EI theta divided by L. This is the total unbalanced moment now. And if we divide this by this distance between the couple, that will give you the magnitude of these reactions. So 6EI theta divided by L square, L multiplied by L is becoming L square. This is how we get this now balancing couple now, 6EI theta divided by L square. Right hand side span we treat the same way. If you see here, the moment generated at the near end, this is the near end now for the right hand side. So this will be 4EI theta divided by L. Now EI and L, these are the corresponding values for the right hand span now. So 4EI theta by L. Clockwise, you can see the sign. To the far end, it will be the clockwise, the same direction, but half of the magnitude. So this is becoming 2EI over L. Now again, we are getting an unbalanced movement from the right hand side, which is 6 plus 2, 6EI theta divided by L. So we need to balance this with the help of this couple now. So this balancing couple will be the amount of this unbalanced moment, which is 6EI theta divided by L, and divided by the span between the two, now these forces, the balancing couple. So this moment arm is L now. So this is how, again, this is becoming equal to L square. Now, the corresponding actions corresponding to the D1 are which one? These are the moments produced now at this one coordinate. And what is the moment from the left side? It is 4EI theta divided by L. And from the right side of this joint, it is 4EI theta divided. So we need to add them up now. Now, both are, if you see, they are in the clockwise direction. Both are positive. So S11 value, S at 1 due to 1 now, it will become 4 plus 4 EI theta divided by L. So this will be 8 EI theta divided by L. And S at 2 due to 1, it will become equal to 2 EI theta by L. Why positive? Because if you see, it is in the direction of the D2, which was clockwise. So S11 is 8 EI theta divided by L, and S21 is equal to 2 EI theta divided by L. How we constructed? We, corresponding to now location 1, we give a unit displacement, which is theta in this case, and we generate S11 and S21. Now, to generate the second column of this stiffness matrix, what we need to do now, corresponding to D2, now we need to apply a unit rotation, which is in the next slide. Here you can see, we come to the coordinate 2, we apply a unit rotation in the positive D2 direction. It is rotated. Now, as a result of this rotation, for this, now how much action is required? 4 EI theta divided by L. At the far end, it will transfer in the same direction by 2 EI theta divided by. Now, because of these now moments, we have one unbalanced moment. We need to balance it with the help of this couple. So this will give you the reactions at B and C. So 6 EI theta divided by L square, 6 EI theta divided by L square. So initially now you need to remember at the near end, if theta is given, how much moment is generated. What will be its sign? So 4 EI theta in the same direction of the theta. How this moment is transferred to the far end by half of amount. So you can find out easily what is the half amount. Then you can come back and you can find out the balancing couple, which will be in the opposite direction of this balancing. So this way you find out these reactions. And this way we generate the S12 and S22. Here, this moment, which is corresponding to D1, it will become your S12, S at 1 due to 2. And this moment, it will become your S22 value. So this way we construct the stiffness coefficient matrix. Now, after having all these three quantities now, what we do, we write the equilibrium equation now. So here now, ADL values we have the stiffness coefficient matrix, and we have this AD values also. So finally, now we can solve this equilibrium equation for the unknown joint displacements. This will give you the unknown joint displacements. When these are known, then we can find out the support reactions if you want. You can find out the member inductions if you want. So we label them, and accordingly we pick the values now. How we will be picking the values of AM, LM, D values. So I'll be telling you those one also, but now the procedure is the standard procedure for the member inductions as we did for in case of the flexibility method. Now member inductions now, how we find out? D we found. After this we come to the process of finding out the member inductions. Member and actions are the moments are shear at each point where it's going to be changed. We can find the member and actions using stiffness method when the redundant joint displacements are known. Now let's illustrate the procedure of finding out member and actions by stiffness method with the help of the above mentioned example as shown in figure. In the figure again you see A, B, C. These are the supports. At A, we have fixed support, B rollers, C roller. Within AB, we have a pointed load P1, and within BC, we have a pointed load P2. We declared this 2 degrees. Why 2 degrees? Because we ignored the axial effects. Now, again, now we are labeling now rotation at B and rotation at C as D1 and D2. D1 and D2, we said the rotation at these locations are our unknown joint displacements. Now specify the member and actions. Now it's your choice how you want to find out which one member you want to find out. Let's shear at A, shear to the left of B, shear to the right of B, shear at C, moment at A, then moment at B to the left and moment at B to the right. Now we declare them as our unknown member and actions. Now somebody can ask you if member at this to the left moment is known, so to the right it is going to be the same moment, so you don't do it. If you don't have time, so you don't go for it, because if at to the left of B moment is known, to the right it will be the same magnitude, but it will be in the opposite direction and they will be balancing each other. So you can avoid such kind of redundant calculations. So when you select them that, okay, now I'm interested in these member and actions, now you go and corresponding values you pick from the process which you have already done. AML values will be coming from where now? When you have basic kinematic determinant structure under the actual loads, from where we generated the ADL matrix. From there you will be getting your AML values, and which is coming here. Look, determination on the of the AML values. AML values coming from here. Look, here we were having AM1, AM2, and this is this basic determinant structure now, kinematic determinant structure under the same P1 and P2. Whatever member and actions you were having there, you include them, the corresponding values with the proper sign in the AML values. And exactly the same process we did in case of the flexibility method. From where we were getting these values when the release structure was subjected to the actual loads. So here restraint structure is subjected to the actual loads. You can pick these corresponding values. Next is the generation of the AMD values. There we did it the AMR values, and AMR values were coming from where? When the determinant structure was subjected to the unit redundant actions turn by turn. So here now the basic kinematic determinant structure will be subjected to the unit rotations turn by turn. So here now you can see AMD matrix, how we generate them. We generate them. This is the actual determinant structure. Rotation is given at coordinate 1 now, corresponding to D1, and we find out the corresponding member and actions now. There the corresponding displacements were found in case of the flexibility method, but here now the corresponding actions now. But there also we were having the actions corresponding to the AM values. Here also we have the corresponding actions. So now AMD11. So this will make now the first column of the AMD matrix. And now in the second step, what we do, we provide a unit rotation corresponding to the coordinate 2 now, which is D2, and find out the corresponding member and actions. And that will give you the second column of this AMD matrix. So here now you can see corresponding to this, the member and actions are provided. The rotation, I mean, is provided. And we find out the corresponding actions now, and we include them as AMD 1, 2, 2, 2, 3, 2, 4, 2, and so on now. Now, after this, what we do, we write these equations, simultaneous equations, and we solve it for the AM, unknown AM values, because AML is known, and this should be AMD actually, not AMR here, this matrix. It is made out of these AMD, so this is AMD 1, and so on. So AM is equal to AML plus AMD times D now. It used to be AM is equal to AML plus AMR times AR, but now it is AM is equal to AML plus AMD times D. And this method will be now explained in the coming problems. The journal now discussion. So when we are specific to the particular problems, having the proper numbers for the loads and spans, so it will be more clear now with this discussion of that method. Now let's come now discuss that how the member rotation or the member displacement is related to the member and actions produced. Now actions produced and members due to unit displacement. Now what we do here now, consider the beam in which is pinned at one end. Here it is, let's say we have a hinge support and fixed at the other end, it is fixed. If a unit rotation is applied at A we are going to provide now theta A now, then the moment induced in the member is shown, or the actions induced in the members are shown. Again here, if you see, this was the original shape, the distorted shape. If we draw a tangent, we are coming in the clockwise. So rotation theta A here is in the clockwise direction. Moment produced, this is becoming our near end now, because here we are providing the rotation. Now this theta A will result a moment in the same clockwise direction with a magnitude of 4EI theta A divided by L. So from here now onwards, you should be remembering that this will be 4EI theta divided by L. Which one? Theta? Theta A. And it will transfer to the far end by half of this amount. So this is how it is becoming 2EI theta A divided by L. And the sense is going to be the same. If it is clockwise, so this will be still clockwise. And then we calculate by finding out this one, we need to keep this structure in equilibrium. So we apply a balancing couple now. This will give you the balancing couple, will give you the direction of these reactions. And you can easily find out the magnitude of this one. In this specific case, it will be 6EI theta A divided by L square. So now prove that MA is equal to 4EI theta A divided by L. This is your class activity. We don't have now time for this class activity. So what I'll do, I'll go quickly over this one and we'll prove this also for you so that you have more confidence. Now, instead of the rotation now, if we give a translation now at one end, so what will be these four member end actions? Now at A, if you see a delta A in the downward direction at A, this translation is given. We pull this down by delta A now. So what will be these member end actions generated? First, how we find out the direction of the moment produced now at this near end. The direction of this moment, if you see, we have shown this in clockwise direction. How this clockwise direction is coming? Simply, if you take this distorted end now, after this displacement, if we take this elastic structure, so this will try to come back to its position now. And because of some force, it will try to come to its back position. So when that action should be in clockwise direction to bring it back. If it is in the counterclockwise direction, it will be taking away even further from this support A. So this is how it is coming back, and it is coming back because of this action which is in the clockwise direction. This way we assume its direction. This displacement was given in the upward direction. Delta A was above this one. So this should have been the distorted shape. Now, because of this distorted shape, if it is trying to come back to its A, so its direction of movement produced will be in the counterclockwise direction. This is how we fix the direction. Now, instead of this, if we fix this A support, and if we give settlement in the downward direction to support B now, so this B will try to come back. So the action generated moment here will be in the counterclockwise direction. This is how we find out the direction of the moment because of the settlement. What will be the magnitude? At the near end, it will be 6EI delta A divided by L square. In case of the rotation, it was 4EI theta A divided by L, single L now. But here, in case of the displacement, this settlement, it will be 6EI delta A divided by L square. Now, how it will transfer, how it will shift to the far end, it will shift to the far end by the same sense now, by the same direction. If it is clockwise, so you can see here at B also it is in the clockwise direction, and its magnitude will be the same. It is not going to be half. We don't take it off. It will be by the full amount. So direction is the same as well as magnitude is the same. In case of the rotation, it was by the half amount and in the same direction. But here it is by the full amount and in the same direction. How we find out the balancing couple now with the help of these reactions? Again, if you see, the unbalanced moment is in the clockwise direction. So the balancing couple produced should be in the counterclockwise direction. This is down, this is up. It is causing the counterclockwise direction. How we find out the magnitude? It will be summation of unbalanced moment. So 6 plus 6 is becoming 12EI delta A divided by L square. And we need to divide this by the moment arm. So this is how we are getting this L cube. So now from this, how we find out the direction of the actions produced and the magnitudes of the action produced, we should be very much clear. Now, with respect to the theta, I'll now verify all these member and actions and their directions. And you can try this for this translation, these member and actions, which are right now on the screen. Now here now, let's prove this, that A is the near end where we are going to provide the theta now. How this member and action produced is equal to 4EI theta A divided by L. Now at the top, if you see now, we have joint A at the left support, joint B at the right support. Joint A, we make it a hinge support, and joint B, we don't allow any translation and any rotation there. So this is a fixed support. So rotation without transverse displacement at one end. We are not allowing this to go in the any translation at A, but we are allowing only rotation here, which is shown here. The rotated shape you can see, and you can see theta A also. Theta A is in the clockwise direction. This is rotation at A. The other end is going to be fixed. We are not allowing any kind of displacement there. And the member is prismatic, having the same constant cross-sectional area throughout. Now, as a result of this theta A, we say MA will be produced at the near end. At the far end, let's the moment produced is MB, general notation we are giving. And the reactions now, look, we are giving now the general reactions. Now, we assume both in the upward direction, RA and RB. Now you can see it's a general, we don't know. Otherwise, as a matter of fact, if MA and MB, they are in the clockwise direction, so you should be having a balancing couple. But no, generally, we assume the direction. What will happen at the end? Negative you will get, and negative, because of negative, you can reverse the direction. Now, if we want to draw the bending moment diagram, so here you see the bending moment diagram. We don't have any shear values, no loading within this span now. Shear is here, RA, shear value here is RB. So if you want to draw the bending moment diagram in terms of this MA and RB, what will be the bending moment here? At A, we have MA now. So MA is drawn. what will be the moment at this, which is MB, and this MB will be equal to, actually it will be MA plus RA times L. This will be the bending moment because of these now MA and RA values. So here we show MA plus RA times L. This is the bending moment diagram for this corresponding figure. In conjugate beam, what we do, the real structure we convert into the conjugate beam. How that is done? Fixed support is converted into free end. Here we free end, and hinge support is in the hinge support. So again, we have the hinge support. So this is the corresponding now. If you see here, this is member AB, and here only we have a hinge support. Here at B we have. So this is the corresponding conjugate beam now. Now, conjugate beam method, in order to find out, we are interested now in finding out the slope here, which is theta A. So for theta A, we need to find out the corresponding shear here, which is RA prime now, which will be the reaction in this conjugate beam or the shear at this conjugate beam. Now, to do that, how we now proceed with the conjugate beam, we now load it with the M or EI diagram. So M we already have, EI is constant. So here we load it. At A we have MA, at B we have MA, RA or L. So the conjugate beam is loaded with the M or EI diagram. Now if we want to take now prime, this is for the conjugate beam we are showing. Here it was RA, but here it is RA prime. So RA prime, why we will be finding out this shear? Because if we find out this shear, it will be giving us theta A now, actually. So once MA and MB, these are known, we can find out theta A in terms of these values. How? Now we find out MA prime is equal to 0. We are in the conjugate beam. At A, we are taking moment is equal to 0. So first we take moment because of this lower rectangular now, which is having length L and which is having this ordinate MA. So what will be the now area? The area of this rectangle, which is MA over EI multiplied by L. Here you can see it in the parenthesis. This is actually the area. So this will give you the load of this rectangle now. And we are taking the moment now about A. So the moment arm for here, it will be L divided by 2 from the center to here, because its resultant will be acting through the center. So M A L over EI times L by 2. This is moment of this rectangle about point A. We are left with this triangle now. Already we used MA now. So this vertical ordinate remaining, it is RA times L. What will be the equivalent resultant of this triangle now? It will be half of RA times L times this distance, which is L. So here in this is written, this equivalent or this resultant is written here, half times RAL or EI times L. And how much is the moment on from the less load intensity? It will be 2/3 of the L now. So here the 2/3 over L is written. Now from here now easily we can find out now MA in terms of the RA and L and EI, or reverse RA, we can find out the same way. So here we found now when we simplify that equation, RA is coming in terms of the MA and L now, which is minus 1.5 MA divided by L. From previous, when we took the summation of moment about A in the conjugate beam method, conjugate beam case is equal to 0. Now RA prime is equal to what? If we go back now, that was the moment about A is equal to 0. Now if we take now the reaction, how much is going to be this reaction? The total load now, it is focusing on this one. It is carried by this RA prime. So it is just the area of this rectangle and the area of this triangle. What is the area of this rectangle? It is MAL divided by EI. And what is the area of this triangle? It is half of RA L divided by EI times L. So we sum them up and we get the RA prime, which is written is MA divided by MAL. This is MAL divided by A plus MALRA. This one multiplied divided by 2. So RA prime is equal to, now RA already we have in terms of the MA. So we put from equation 1 the value of RA here. When we solve this, so RA prime is equal to now MAL divided by 4EI. But now we know that slope in the actual structure, it will be equal to the shear in the conjugate beam. So RA prime, actually this is equal to theta A now. So we replace this RA prime by theta A, and it is equal to MAL divided by 4EI. Or if we rearrange this, so MA is equal to 4EI theta A divided by L. So this is how we get this famous number now, that MA will be related to this now theta A by this relation. At the near end, the moment produced will be equal to 4EI theta A divided by L. It is in the same direction of this theta A. Now, if we substitute this value in equation 1
सर
now, yeah.
सर सर वो हमारा हमारा दूसरा क्लास अभी स्टार्ट हो गया है, तो सर ने कॉल की थी कि बस आप लोग आ जाएं।
किस वक्त तक आ जाए?
सर अभी अभी हमारा क्लास स्टार्ट है ना 11 बजे।
अच्छा, इस तरह है ना कि ये तो प्रूव हो गया ना, बस मे बी आई टेक लाइक 2-3 more minutes and then we are done for today.
ओके सर।
ठीक है, तो क्विकली आई विल फिनिश इट नाउ। अब अगर आप क्या करें, एम ए वैल्यूज आप यहाँ पे आप पुट कर लें, तो आर ए इज इक्वल टू, लुक, minus sign is coming, so it means we assumed RA in the upward direction in the actual structure, but negative is, it is showing it should be in the downward direction. From equilibrium, अब B पे इसका क्या होगा reaction? It will be balancing this RA, so it should be in the upward direction. MB कितना होगा? Now you can take, now RA है आपके पास, you have MA, you take the equilibrium at B now, so you end up with MB value, which is 2EI theta A divided by L. So all the 4 now member inductions we proved with this exercise. Now fixed inductions आप कैसे मालूम करेंगे? As I told you in the start of the class, there for the more general cases I will be giving you. Now if we have this fixed end condition, in the middle at L by 2 we have P. So member inductions generated, the moments will be PL divided by 8, PL divided by 8. You can see the directions also. And the reactions also, you can see the shear also, P by 2 and P by 2. Now, if the same L length beam, but it is with UDL, so the member end moments will be WL squared divided by 12. And the reactions, these vertical reactions will be WL divided by 2. If you have this condition, fixed end at certain distance A, if couple is applied, so the balancing couple, this will be MA/MB, and how we find out MA/MB equations are here. And for the vertical reaction at A and B, you have the equation. If it is with the triangular load, so with the less load intensity, which is point A now, RA, the vertical reaction we find with this reaction at B, we find with this equation, where P naught is now the maximum load intensity. Moment at A we find with this equation, moment at B we find with this equation. If P pointed load is off center, let's say L by 3 now, we already have the case of A and B, we have the equation PAB square divided by L square, something like that. So here now these values are given. Then if we have 2 pointed load at 1/3 location, these will be the member inductions generated. If we have a couple now within the member at midst, and these will be the member inductions generated. And this is all about today's lecture. So the member inductions, you can go for the quick references and you can memorize them also for the most standard cases. And that way, very easily you can find out your stiffness coefficient and the ADL matrix you can generate. Any question now?
सर वो असाइनमेंट के क्वेश्चन नंबर 1 में एक क्वेश्चन था।
نہیں assignments تو آپ نے کرنے ہیں نا, آپ سبمٹ کرائیں گے, you lose the marks also and then we discuss it. Otherwise you should
اوکے
be struggling.
اوکے سر.
ٹھیک ہے, آج کے لیکچر میں ہے اگر questions ہو you are most and welcome, آپ کریں.
نہیں سر آج نہیں.
You turn on the mics now, you can turn on the mics and you can ask me if you have any question. So silence means no question, right? Now, next
یس سر.
class, inshallah, we will be solving 3 problems on having this. So you should go through all this process, how we find out these member indexes and all these things. And then we involve the settlements and all these rotations and settlements will solve problems. And before midterm, then we will be done with the course. So the following then lecture may be about your midterm examination. So how the midterm examination will be conducted? So in next lecture, I'm going to guide you.
اوکے سر.
Okay. So now take care from my side, and now this is the end of the class. Okay, bye.
تھینک یو سر.
تھینک یو سر.
وہ سب سن لے, دوسری کلاس میں 11:20 سے پہلے نہیں جانا. 20 منٹ 15 منٹ بریک کر لیتے ہیں, ٹھیک ہے؟
سب نے جوائن
صحیح
جائیں
ہے, صحیح ہے, لیکن یہ اسائنمنٹ کب میٹ کرنا ہے؟
ڈیٹ گزر گیا بھائی.
صدام
صدام
جی برکتا
ایک تو آپ کی کویشچن ختم نہیں ہوتی, 10 کے اتنے زیادہ کویشچن اسائنمنٹ ہے, اسائنمنٹ کل سے لگے ہوئے ہیں.
برکتا
میٹ تو کرنا ہے نا.
جی
چبل کلاس اسٹارٹ سے جاؤں میسج ہوگا.
یہ سب کتنا
بل کلاس 11:20 میں وقت کے مار اٹینڈ کوئے.
11:20
خبر
میں
کیا
ساڑھے
جی
11 بجے نمک کے
11:50
مارٹن کا وے
11:50 نا
نہیں 11:50 نہیں پھر تو
سر بلا گیا ہی حالت ہے
سر
حالت بیٹھ ٹریفک جوڑ کڑے کچھ
11:30 بجے سے پہلے نہیں آنا ہے دوسرے کلاس میں.
کیمرے
صحیح ہے
خان کے
صحیح ہے.
گرو نمائنا کیمرے آن کے
ہاں عمران کے
انسا
میرا کلاس سٹارٹ تھے وہ 11:10 15 سے.
اے نعمان
انسا
نعمانا
مولا خدا بیک کیمرہ دو دا فرنٹ کیمرہ سرانگے روسی
سوئچ کیمرہ ہوئے, سوئچ کیمرہ آپشن بنا سے
دیکھو گپ لگے ہوئے
ماشاءاللہ
نمانا مولا
سروس
کیمرہ
کیمرہ
راضی
فرنٹ کیمرہ سرانگے روسی
فرنٹ بیک کیمرہ کو نہیں مڑا سرنگی بیک لگی
برکت رالو
دا
کے
مولا کیمرہ سرانگے بے فرنٹ والا نر
برکت رجیب دناستے برکت
دچے دا غاد مال کوٹا مال نام دے
آپ دیر کرٹیکل سچویشن جناستے تھا
قسم دے بالکل لگا دا وی کنا لیپٹاپ کی مڑا بیک نہ ہو جی نرسی کیا بڑے ہیلو نو انسا انسا ہاں
برکت ہے
اسے لگ گیا تھا پر
ہاں دا بیک کیمرہ اندو فرنٹ کیمرہ نر
لیپٹاپ
روسی
موبائل لگے کہ لیپٹاپ
لیپ ٹاپ کی بیک کیمرہ چیر تو
لیپ
لیا
ٹاپ
یاره قسم ته څه په غم سره وښتي.
انس کوم دي راغلی ته
قسم ده نه
یې
راته
ته اوس
یا ته
رښتیا خو نه وایې انسه.
دینه کسا دینه دا کیمرا مې آن کړه.
دا لیپټاپ ته په لټاپ د کیمرا دم چې فرست ټایم ورته. اے سجاد
یاره بس پته نه لای په نن کلاس کې ویډیو ډېر
سجاد
سوي نه
سجاد نشته سجاد
बोलो बोलो
और सारा कैमरा यार तू बात क्यों नहीं कर रहा है? हम कमेंट सेक्शन में वो क्वेश्चन डालते हैं.
देखा यार तू क्वेश्चन पूछता है कि सर से पूछो ये करो वो करो तो मैं सर से पूछता हूँ ना तो इस तरह तब नहीं होता क्या.
सजाद आप कौन सी जगह है?
ये तो चित्रालय ना
तो वहाँ पर नेट काम करता है?
ये मैं थोड़ा हाँ ना अभी आ गया ना अभी मैं थोड़ा वॉक के लिए जा रहा हूँ फिलहाल लेते हुए वॉक करता हूँ थोड़ा.
नहीं आप चित्राल सिटी
मोबाइल पे लगे हो?
हाँ मोबाइल से लगे हैं.
أنا سسوى يا كنا
नसा तुला फ्रंट कैमरा नाम की जुएल
برکته
जी
سهل ده
बस नसता का म्हणाला अल्लाह फजल दे तो जाए बच्चों. ओ मस्जिद है मस्जिद सिर किस दिखून की नसता है. तुम्हारा तुझा वीडियो लेके
वीडियो ना कैमरा ما خپل کیمرا ده ما ته فرانک خپل ځان ښکاري تاسو کیمرا افتونه اته ولا دا په ډیر زیات غره موسم ګډوډ بلاوالي
حالات خرابتي
حالات خرابتي کنه دا کیمرا خراب ده کړه زیات
حالات مکمل ګډوډ دي.
نه نه کیمرا خراب ده لیپټاپ देखिए
دا زیاده ده.
انا ستاسو په بعد کې
نه په کلی کې نت چیرته شته په کلی کې موبایل سیګنل میږ نه ویني.
دا ابو ذر به څنګه پوسټونه کول ورې باشه خان کوټ نه زیره کې ویلې
ابو ذر خو اصل ته زیره ماشاءالله کوم مکمل درته ویل ده.
ای په زیره کې دک دا وړه راته یاد ده سوې
تاسو وایي
بیا څو خیل خو نه درته یو ده.
انا څه یو خبر مې نوٹ کړه انس فاروق برکت وزیرستان فاټه ریزن چې نه راځي بنول دي
دا خدا
نه دا دومل و دا غجانی کې من کلی خو کنه په غشه دی وزیرستان کې دی شولې لکادو
وزیرستان میرلی نشو کېږي
می شوالی می شاول په بیسیک کې یادو وین سي چای سره تر موږ کې غلای نه ته خو خالي سٹارټر سره وغلې
دا څه خبرې به زه بدل ولې زوري غپور لاړ کنه ګور پر لاړ
شاشا جنوبي ته وته لوي
جنوبي کانګرم په درزمت نه لاړو ول مکین لدا په کانګرم امیر شاه ته موسن داور سره ملاقات کړه
بس فری
موسن داور ته
حالا موسن داور سره ملاو شوې
ملاو شوې دا ټاګه شات مولا بس سیاسي پولیټیکل کې ډیسکس
زبردست بچی لکه چې سیاست تر وځي اراده دې دا شي دي
یاره مکمل سیاسي شو دا سړی خو
اراده خل دي نشي
تاسو به ووټ راکو
इंशाल्लाह Awal zal. Among load
فاروق
das rawali ka kuje. Khabar tha ko Quran de to Facebook pe wona gode otina agna stage rasa hai. Direct
نه نه
code
غټه
goda
غټه
der kavi hai.
یاره په فیسبوک باندې خو سړی صدام او عبید خوځلې ونه کړه
صدام وبعد
Kashan do numand no sa numand pe sar da post no ke na ke dai ha body god se da kya vida maratun kon ko tip se check karzi.
ما
Ke
یې
pele
ته
sa yu.
دا سلی ما ته بل څوک میسنجر ته وایي یار ما ته وټ غوړې زه یو دوه نه ښکارونه پر منشن کنه زه به تاسو چې کوم منشن کوم تاسو به ماین کوم بل څوک به ماین کوي به تاسو چې کوم کوم مطلب تاسو په نت نبی تاسو په نت دی تاسو ته وګورئ نوټیفیکیشن نه دی به زما چې ته خالد کارا سي چې وټ پوښتای چې دا
No bet me yuri bayat pero ene black. To black ke de bia.
عبید و صدام مو پلاک کړی دی په میسنجر باندې
Messenger na pe Facebook में black kadi di chala mana kafi jo kida. Next class क्या बोला गया इनवाना next class तक से क्या बोला next class तक से
नेक्स्ट क्लास ना बड़ा गपला गवी
تاسو یو
ना ना
नेक्स्ट क्लास से तारीख सर बंदा
transportation
लेवाना टीचर ने राखो बस ना नेक्स्ट क्लास का रहता है
دا स्ट्रक्चर د लेक्चर
से
دا وګورئ
बस वैसे ही है
हमको प्रोसेस करते हैं और हमें आउटपुट 3 मिलता
कारीगर दस
है एवरी टाइम वी गेट अ डिफरेंट आउटपुट एवरी टाइम तो अल्टीमेटली क्या करते हैं जितने भी आउटपुट है इसको हम एवरेज करते हैं और इससे फिर हम एक आउटपुट